just play like.
Okay, I think this is it. Okay. Sorry.
Okay.
So today we're going to be hearing from Mary Beth Greer, and I'm going to read the program that she's in because it's very, very long. But she is doing a master's degree in the Executive Management for Design and Construction program, and she's also a project manager here at Northwestern Facility. So we're going to hear her experience and really the behind the scenes of water at Northwestern and what's fueling the research here. So maybe you'll recognize some of the ways that you use water in your research, but for those of you that may not be involved in research, this will be a good insight into how necessary water is tangibly here at Northwestern. So please help me welcome Mary Beth.
All right. Well, thanks for having me. Super excited. So yeah, so I'm in McCormick doing a grad degree, and then I also work in facilities. So we're over at Ridge 2020, which is kind of right across like the Foster stop. And so we kind of manage all the design, construction on campus. We work with the shops who keep your buildings running. And I'm kind of our campus engineer. So I come from a mechanical background. So a lot of our project managers come from architect side or construction side. And then I get to pester them about how fun infrastructure is and why they should pay money for it, which they love. So it's been super fun. So like if you've seen KEC, Kellogg's, or ADC now, Kellogg's new building, we're working on that. The Jacobs Center, I was over there this morning. So we kind of do everything from new projects to underground piping. Really depends on the day. All right. And we'll see if I can like arrow.
Yep.
Okay. All right. So I'm going to start. So it's like show of fingers, show of hands. Like how many types of water do you think are in a research lab or could be in a research lab if you really maxed it out? 4, 4, 3, 4, 5, 5. Okay. All right. So we're a little low, but you're at least more than like one. So that's promising. So kind of want to go through, and I will be honest, this is gonna be a mix of construction and then fancy architect photos because apparently they don't like the sink so much. So right here, what do we think we got? How many? 3? That's pretty good. So right here alone, we've got DI water, which is your like ionized water that you use to clean things. You can use it for samples. Domestic water, we've got hot and cold. And then here, which is hiding a little bit, we've got our eye wash station, which is tempered water, where we usually, for safety, have to mix it to be 70 degrees so you know you don't burn or freeze your eyes, similar to safety showers. So now we go here and we add the fume hood. So now at this point, we start to add kind of cup sinks. So even your fume hoods have waters. And the thing we want to remember with water is it's always got to go somewhere. So a lot of times there's also drains too. And technically that also counts for water. This is your basic. So now we'll level up. And I think it's funny. I think Laurel said she is in anthropology. So this is actually above ceiling of Jacob's new anthropology lab. So this is now where we get to the HVAC side. So HVAC is your heating and cooling, and that is different from like your sink water. And so HVAC, if we start to look here, we've got a couple different things. These are our chilled water mains, and those then serve what's called a chilled beam. And so the reason HVAC water is different than domestic water is because HVAC water, you put chemicals in, you don't want to drink it, it circulates around your building, and it's more for heat transfer versus domestic water, you know, you can shower in it, you can drink it, so we isolate those systems. We also have here, what you can kind of see, is our sprinkler water. So fire suppression water is also a different type of water, and that usually has to be really high pressure to make sure that if there's a fire in the building, you can get water there immediately and for long enough that it actually puts out the fire. So even here alone, there's some other water. You know, we've got some hot water going back here to get to your hot water coil, but that one you can't see well in the photo. So then again here, even in your finished space, right, when we talk HVAC, these are kind of what those chill beams look like after the fact. So when you see these up in the ceiling of a lab, that is your cooling. So there is water running through those coils, and that's actually how you're cooling the room. Um, so now we get to the mechanical rooms, right? So you've got to have kind of a central place that sends out your water and your heat and your cold. So how many types of water do we think are in this picture alone? A lot. So from the picture alone, there's about four. And I cheated a little. So right here you've got your chill water. And so these are the coils that go to your big air conditioning units that then bring air to your little units in your room. Here you can't really see very well, but you've got your hot water, and this unit's actually glycol hot water, which means we add chemicals to it so that in the winter it doesn't freeze. Because I don't know if you went by like SEP fraternity earlier this winter. They had a nice exterior waterfall feature that was frozen, and that's what happens when pipes burst, and maintenance doesn't love that. This room's also interesting. We'll talk more about it, but they've got an RO skid here, and then they've got purified water in the corner, which is not typical for all our buildings. Yes. Did you say RO? Yes. So. Yes, absolutely. So we can get to those now. So the question is, right, like what do all these, who uses everything and what does it all really look like? So domestic waters, we said, is mostly like your bathrooms, your sinks. That one's kind of when people think water usage, that's the one they typically think of. So like here is your safety shower, eye wash, drain. And this is where eventually they're going to put in a sink. You've got your little hot water stubs and your drain, and your little hammer rester so your pipes don't bang in the wall when the water turns on and off. And then this one is just vent to get all the stinky smells out of the building. So there's a lot of piping that goes behind domestic water distribution, but that's kind of the easiest one for people to visualize. So now we get to HVAC equipment. So these are better pictures. So with every air handler, kind of no matter how big or how small, we have kind of two sets of water that goes into it. We have heating water and cooling water, which are different than domestic hot water and cold water. And it's a closed loop. So where domestic water goes down the drain, heating water and cool water you want to recirculate through your building. So here, these are all kind of different versions where you can see kind of the chill water supply going out and coming into our units. Here, this one's hot water return. This one actually also has a steam coil. So steam is kind of the old way we made hot water, where you did really high pressure steam and you distributed it through buildings, and it's really efficient. But nowadays, we don't like making steam as much, right? As we go to more sustainable solutions, a big take is, right? So UVA, where I used to go and where I used to work, we had a dedicated coal plant with a dedicated train that drove into our coal plant so that we could make steam. It's a very energy intensive process to get water to be 400 degrees. It takes a lot of energy in. Northwestern, we still do have steam distribution. And so one of the things we're working on, is we don't use coal here, so we're better than that, but we do use natural gas still for a lot of the creation. And the question is, right, how, if you can't get rid of it completely, how do you make it more efficient so that we're losing less water? So that's a big topic in the industry, is the conversion from steam to low temperature hot water. And so in the future, what you'll probably see is at some point, we're going to dig up a heck of a lot of campus for some piping mains. And that's when you're going to go from, your 12-inch steam main that feeds all of North Campus to your 22-inch water main, because it just can't carry as much energy. And so in an underground application where it's already really full, how do you fit those pipes? And so that's a big question. So until we can pay and find the space to fit all those pipes, it's how do we use our resources as efficiently as possible. And then steam, once it kind of goes through the system, it loses some of its energy, so it condenses. So you still have really hot water, but it's not in vapor form anymore, and that's condensate. And condensate is like, people call it like liquid gold. Like that's super hot water, still a lot of energy. And so we send all that back to our central utility plant, which is kind of like Have you all ever walked past or like along the lake shore and seen that building with the weird pyramids at the top? That is our central utility plant. So inside there are all of our boilers and chillers, and that's the place that makes all of the steam for campus and all of the chill water for campus. And from there, everything network distributes underground. So you want to get as much condensate water back to them so that they don't have to take new water, heat it all up again, and then send it out. They can take the mostly warm water, heat it up a little bit, and then send it out. So that's how on a campus skill, we try and make things as efficient as possible. And a fun fact about our chillers is because we're actually so close to the lake, they can use Lake Michigan water to cool down our chillers a little bit. So, yes, question.
I have a question. You mentioned the piping that we're going to go from smaller to larger piping.
Mm-hmm.
I would expect if you want to collect or distribute more effectively, we want smaller but more piping. Is that not? Can you explain why we want kind of these bigger ones, or is that just a centralized big one that connects to all these smaller underground pipes to reach to distribute steam and then collect that condensate?
Yeah, that's a great question. So, right now, the way we are laid out is everything starts at cup and then it comes in what's called tunnels. So we have, and actually, let me skip really fast. Tunnels. So these are underground, and these are your pathways. Some of them are walkable tunnels, some of them are not. But it's helpful when they're walkable, so when things leak, you can actually fix it. The ones that are totally underground, when it leaks, it's a lot of digging. So this is our medium pressure steam. This is our condensate fire protection, and then chill water goes through here too, but you can't see it as well. So right now, they've sized the pipes for the amount of energy that needs to go to all the buildings. So, right, we have one main pipe that goes, or two main pipes that go north and one main pipe that goes south. And then from there, it branches off to all the buildings and there's little loops. And maybe after the fact, I can like send out our GIS map or something so you can see all the pathways. They're kind of fun to look at the routes. When we go in the future and take that steam away and try and distribute hot water, because it takes less energy to make hot water than steam, those pipes have to get way bigger because you have to get the same amount of energy to those buildings. And so then the question becomes, do you send multiple smaller pipes and reconnect the buildings in different ways? So maybe one pipe serves 5 buildings, maybe you do 2 pipes and one serves 3 and one serves 2, and that helps you out. The problem is then it becomes a space game, right? Do I have the space to fit 2 pipes underground, knowing that underground I have water, I have sanitary, I have electric, I have all our IT stuff. Like when you start digging underground, we get crowded really fast. And as you all probably figured out, water and electricity don't really mix. So there's lots of rules about how far things have to stay away from each other. They don't like it when you put your sewer drain on top of your domestic water, so things have to get stacked different ways. So there's a lot of rules about how things go underground. And admittedly, in the past, people weren't very good at exactly marking where they put it because they're like, oh, you just dig and you put it there, and people will know. And then guess what? 60 years later, no one really knows. So you play a lot of the game of like, it's supposed to be here. Where is it actually? And so like we have a guy on campus at Gardo who basically has the underground utilities mapped in his brain, and we are working as facilities to get that mapped onto paper, because he's great, but at some point he will probably retire. But he will go out in advance and actually like spray paint on the ground and be like, all right, this is your chill water here, this is your gas line here, don't mess them up. So that's a huge question though. But like the how it reconnects, we are paying a lot of engineers a lot of money to figure out what is the best way to reconnect. And there's no one right answer. So at the end of the day, I think it's going to be a lot of combinations of things. Yeah.
Do you mind if we interrupt you?
No, by all means, please go ahead. Yeah, ask us questions.
And then let's interrupt to say that we have a compost bin for the utensils and the plates, not in the plastic, but there's a green compost bin during the
Yeah. All right, so then this is more the lab section. So, what does the water actually do to serve research at Northwestern? And the answer is everything. Like the more we started talking to people, the more we realized like everyone's using their water in their own ways. I don't have a photo, but like the concrete lab made their own little like slurry fountain so that way they could mix concrete appropriately. So this is process chill water. And this is kind of a different form of HVAC water in that most of our HVAC water goes to the equipment that heats and cool your room. Process chill water goes to the equipment that is in the lab. So right, that heats and cools your researcher equipment. So we're talking lasers that get really hot. We use process chill water to cool those. Mass spectrometers, so like if you're separating ions, those get really hot. Again, you need to have them cooled, otherwise your whole experiment gets kaput. The powder X-ray diffractometer, crystals, it has to be cooled by process chill water. So pretty much every piece of major lab equipment is either being cooled by process chill water or it's kicking off that heat into the lab, and your room HVAC has to be really big to then account for that. Sometimes you'll hear there's issues with the process chill water, so like IMCIRC, their equipment sometimes overheats, and that's a problem for them. So that's when like facilities has to come in and be like, okay, why is your loop not working? A big challenge is researchers really like to buy old equipment off eBay and then just hook it up. That makes it really dirty. So we use things called heat exchangers, which is kind of like a plate that says water can go in this side and water can go in this side, and they can transfer heat, but they can't touch. And that's basically just to keep the dirt out of our system. So there are a few notorious researchers around campus. If you ever hear people buying things off eBay, be like, hey, heat exchanger. That's my plug. But there's a lot of researchers doing really cool things, and like it gets to the point where like even they know their water systems, which is pretty cool. Um, so then the purified water, so that's this system. That's a very specialty, very regulated water, and that is water that goes for the vivariums. So we have a lot of vivariums on campus. I think Hogan alone holds the like amphibian vivarium, which apparently has really massive frogs. They're super regulated, so you're like not really supposed to go in there, and they're usually on lockdown so that PETA doesn't protest. But in there, like they're doing all sorts of crazy experiments. If you remember this summer, they put rats at NASA on the space station for a sleep study. Northwestern was the control rats. So like those rats, they love more than like I get paid. Like let's be clear. Which means they need really clean water because right, the last thing you want is like the rats' drinking water supply gets contaminated and now NASA's experiment has been messed up. Like that's not what you want. So they have quality control for that, and it's basically like a chemical tank system that goes through, and then the meters report out like the purity level and the quality, and it all gets tracked. And that's so that way the animals can be happy and well cared for. Um, um, so then we talked about steam and condensate. We also still do have some steam usage on campus. We're trying to get away from kind of the little steam loads because especially with an aging workforce, people don't really know how to maintain steam, and steam inherently is a little dangerous. So right, water will burn you, steam will really burn you. It's like 400 degrees and high pressure. So a lot of things like these are sterilizer units, which basically sterilize equipment. They just did a big push on campus to make all of these electric. One of the big things around Evanston, though, is if you've ever noticed, our power is really inconsistent. So that's part of the conversation too. Is we start putting everything electric on the grid. The grid already can't keep up. What happens when that actually goes down? So there's a lot of talk of like backing up, and that's why the efficiency is so important of it all, because we're never going to be able to get completely away from everything. Um, this is a fermenter that one of the labs is using that uses steam. And they're doing, I want to say it's bio inorganic chemistry, which is above my pay grade. but they had a lot of really cool diagrams. This is from one of their research papers that they put together. But even they, right, like you got to figure out the steam connections, and then you can see it goes through the trap and then it turns into condensate here. And they're using that to kind of power the steam powers the equipment a little bit too. So because it's such high energy, you can use it in place of electricity sometimes for small things. So we do still have use cases even beyond just kind of an HVAC. And then RO water. So RO water is similar to DI water in that it's purified. It's just purified through different filters. A lot of times they're pretty interchangeable. It kind of depends on like what specifically the researcher needs. And so it goes through a bunch of filters. And RO water, the way that's really easy to tell if you're looking in the ceiling is if it's stainless steel or plastic pipes. Because RO or DI water is so pure, if you use like a standard copper pipe, it'll eat right through it, like within months. Same thing if you were to ever, this is Dave. Dave does all our metering. Dave was my model to show how big the RO water tank is. And this is one of the small ones. Like Cook Hall's one goes all the way up to the ceiling. It's massive. So he was saying, he needed to check one of his meters the other day. So he took some RO water, put it in a cup, walked to his office that's like 3 steps away, put the meter in, and he's like, oh, it's not working. And then he realized that just in the time it took to walk to his office, the RO water was so pure that it was pulling ions out of the air and reionizing itself. So it will literally it will leach from anything it can. So you've gotta be very careful. But we use that a lot in like our glass polishers. So that way you don't get contaminated equipment. We'll use it for humidifiers. So like if a laser lab has very strict humidification, because you don't want to get like calcium buildup in your air. So if you ever see like white on your humidifier, even your one at home, that's calcium. We'll use it, and then we'll have taps for it in the labs. I mean, the researchers can kind of use it how they see fit, and it's kind of on a case by case basis. A lot of petri dishes. And so then I guess these are kind of the top 10 was what I went for. Water types that we talked about. So the hot, the cold, the tempered, and the fire suppression are kind of your plumbing side. And then your steam and condensate. And then I guess HVAC, there's so many different types of water, but it all just gets divided between temperature, pressure, and purity. And those are kind of your 3 things that dictate what it is, and chemical makeup. So, right, we have one guy on campus, Mike Fair, who goes around and will test all the water compositions to make sure everything's doing the right thing. And then he'll come in and add chemicals where needed. So he does that per actual individual loop. It's not a one size fits all. So you can get so many specialty water types just based on what the actual research needs or what the building needs. Different ages of buildings need different levels of care based on how old their pipes are. So it's a bit of an art and a science when you get to the point of HVAC water. And then I just pulled some stats, domestic water usage on campus, and this is not complete. So this is only what we have as Northwestern meters. Most of Sheridan Roadside, like across Sheridan Road, that's not metered. That's metered by the city. North Athletics is metered by the city. You can see even just 3 months in, we've already used 25 million gallons. Like that's a lot. Since 2020, and you can see we've also been pushing to improve our metering process. It wasn't that we were using this much water in 2021 and what the heck happened in 2025. We've just started adding meters to the system because we've realized water is really valuable, and so we should track it. But we're already at 423 million gallons of water in 5 years. That's a lot. So like Norris swimming pools, that's like 457 Norris swimming pools, and that's a big swimming pool. So we use a lot of water. That doesn't even account for the HVAC. That's just like what we get through the city. So you can see it's a really important resource. Yeah, very fun.
Thank you so
Cool.
much.
Well, thank you all. This is super fun.